So in a previous video, I went in detail through some of the factors that stabilize carbocations, and in this video, I want to put it all in perspective. So let's just go through the different factors that stabilize carbocations, and then we'll have an overall picture of how each of these factors influence carbocations, put it all together, and have a general list that you can use to figure out which carbocation is more stable than another. So in the previous video, we talked about the three factors which stabilize carbocations. Number one was substitution. Remember, carbocations are electron-poor species. Being electron-poor, they are going to be stabilized by neighbors that have high electron density or are electron-rich. And for our purposes, we'll consider alkyl groups to be electron-rich. So the tertiary carbocations are going to be much more stable than secondary, which are in turn much more stable than primary, which are much more stable than methyl. Methyl being CH3+. We also said that resonance was another factor that stabilized carbocations. So if you have a carbocation with an adjacent double bond, it can be stabilized by resonance, and this is going to greatly stabilize your carbocation. The third factor we said was adjacent lone pairs. So if you have a carbocation and you have an atom next door which has a lone pair, that lone pair can donate to that carbocation, give it a full octet through resonance, and then actually every atom will have a full octet. And there's one factor which I didn't mention which actually destabilizes carbocations, and then that's important to mention. So far we've only really talked about sp3 hybridized carbocations, and sp3 are actually much more stable than sp2, so that would be a carbocation that's directly on a double bond, which is actually much more stable than an sp hybridized carbocation. And this has to do with the fact that the more s orbital character you have, the closer that orbital is to the nucleus. Remember, your nucleus is positively charged, so you have a positive charge adjacent to a positive charge. This is going to be a destabilizing factor. So for that reason, sp3 hybridized carbocations are more stable. So let's just draw it out overall. The overall pattern goes something like this. So you're going to have CH3 at the bottom. This is the methyl, and this is less stable than primary. Okay. And then this is going to be less stable than what we call allyl. Now allyl is, this is an example of a primary carbocation, but it's resonance stabilized. So this is allyl. And then we have, this is about the same as benzyl, about the same, benzyl, where we have a benzene ring attached to a CH2+. So again, this can be stabilized through resonance. And moving over, we've got, oh, looks like a remnant from something I just erased. We've got secondary, and these are also about the same. So C+, CH3, H, CH3, so this is secondary, 2', which is less stable than tertiary. So CH3, CH3, CH3. Okay, so this is the general pattern, tertiary, actually methyl, and primary. Now, there's two other things that should be put in here as well, and this is very important. So, as I mentioned earlier, sp2 is very unstable if it cannot be resonance stabilized. So, for this reason, a carbocation that's directly on a double bond, we call this vinyl. It's very unstable. It's about as stable as a primary carbocation, so considerably less stable than allyl. There's no resonance. No resonance. And similarly, there's another type of carbocation. If you have it directly on the ring, it's essentially the same as a vinyl carbocation. This is called a phenyl carbocation. There's also no resonance. There's no resonance because the plus charge is actually out of the plane of those p orbitals. It's in the same plane as those hydrogen atoms. So there's actually no resonance you can draw to stabilize that carbocation. So sometimes it's a little hard to see, but make sure you can see that there's no resonance that can stabilize that carbocation. So these are about as stable as primary. So for that reason, in SN1 reactions, you never want to draw a leaving group leaving to form a vinyl or phenyl carbocation, because that will be really unstable. In the SN1 reaction, groups that could be plausible would be, for example, you could have a primary allyl chloride or halide, which may leave to give you a carbocation, benzyl. These can also participate in SN1, and secondary, but of course tertiary would be the substrate you'd be most likely to see in SN1 reactions. So where did these numbers come from? This might just be of interest. I'll just put it up. You can just pause and have a look at this. But this just comes from the measurement of dissociation energies, and you can see how we go from, this is the most unstable, this is the most difficult hydrogen to remove, and going down at the very bottom, go from methyl down to, here's our primary, here's phenyl and vinyl, primary allyl, secondary, actually benzyl is a little bit more stable than secondary, but for our purposes about the same, and then tertiary at the bottom. So that's from March's Advanced Organic Chemistry. These numbers have been measured, and we've done some calculations based on these measurements. So just out of curiosity, thought you might be interested.